Hi guys, this video is going to be solving problem number 1223. You can see we got a circuit here with 3 capacitors, 2 of them in parallel and 1 of them in series with those other 2. The question asks first, what's the equivalent capacitance of the circuit, and then what's the voltage across each of the capacitors. So let's get started. To find the equivalent capacitance of this circuit, first thing we'll need to do is find an equivalent between C2 and C3, and then find an equivalent between that new capacitance and C1. The equation to find the equivalent capacitance between 2 capacitors in parallel is just the sum, and then once we have that new equivalent capacitance of C2 and C3, we'll then be able to find the equivalent capacitance of all the capacitors. Our first equivalent is between C2 and C3, and because they're in parallel, we can just add them up as per the formula. So 330 picofarads plus 470 picofarads is going to give us an equivalent capacitance of 800 picofarads. So with that new equivalent, we now have a circuit that looks like this, where you have the 30 volts here, 20 nanofarads here, and our equivalent capacitance of 800 picofarads. So because those 2 capacitors are now in series, we can use this equation here to find a new equivalence. I'm going to use the shortcut, which allows you to take 2 capacitors in series and not go through that whole reciprocal equation. So the equivalent capacitance between C1 and our new equivalent C2, C3 is going to be 20 nanofarads times 800 picofarads over 20 nanofarads plus 800 picofarads. This is the same sort of style as using the parallel resistor shortcut. So plugging that into a calculator, our new equivalent capacitance is 0.769 to the exponent -9, or 0.769 nanofarads. So that answers the first part of the question, the equivalent capacitance. We found it to be 0.769 nanofarads using first the capacitors in parallel equivalent equation here, and then secondly, once we had that new equivalent of 800 picofarads, these new capacitors are in series, we used this equation here. If there were more than 2 capacitors in series here, I would have to use the full equation, but since there were only 2, we could use the shortcut rule and get our answer of 0.769. So in order to solve the voltage drops across each individual capacitors, we can use an equation that's very similar to the voltage divider rule for resistors in a series circuit. As you remember, the voltage divider rule is V1 over E is R1 over R total. So if you had a power supply with, let's say, 2 resistors, one of 5 ohms, one of 15 ohms, and a supply voltage of 20 volts, you could solve the voltage across R1, the 5 ohm resistor, by just plugging in the values like this. RT is 5 plus 15, or 20, so V1 over 20 is 5 over 20, and if you just rearrange, you'd get a voltage of 5 volts. So we can use a similar equation when solving for voltage drops across capacitors in a series circuit. It looks very similar to the voltage divider rule, except instead of having, in this case it would be R1 over R equivalent, they're flipped. So the equivalent capacitance is on the top, and then C1 is on the bottom. So you see how the second part of that equation is flipped. You would expect it, if we were dealing with resistors, to have R1 on top. With capacitors, it's C1 on the bottom. So why don't we just plug in some values and solve for voltage drops across these capacitors. This diagram here is the C1 and an equivalent capacitance between 2 and 3. Those two capacitors are in series, and thus we can use the divider rule. So let's plug them in. V1, that's what we're solving for. We're solving for voltage across capacitor 1. E we know as 30 volts from the power supply. The equivalent capacitance we found earlier at 0.69 nanofarads, and the value for capacitor 1 is 20 nanofarads. So let's plug it in, and we get 1.15 volts. So V1 is 1.15 volts. Cool. So we would expect then the other equivalent capacitance to have a voltage of like 29, right? Because voltage in series adds up. If the total voltage is 30 and we just found this to be like a little more than 1, we would expect this to be like a little less than 29. So let's try it out. Rewriting our voltage divider equation with V2 in this case equals equivalent capacitance over C2. So V2 over 30 is the same equivalence capacitance, the entire circuit at 0.769 nanofarads, and our C2 is 800 nanofarads. Remembering that that 800 came from an equivalent between two capacitors, the 330 and the 470 picofarad capacitors, and finding an equivalent between parallel capacitors, you just add them up. So in this case it's pico, not nano, and can plug those values straight in. So cool, yeah, that's what we predicted. We predicted a voltage slightly under 29 because the voltage across C1 was a little more than 1. So let's jot that down. V2 is 28.84, about 28.84 volts. So just to double check that everything's in order here, we're expecting that the voltage from the power supply is going to equal the sum of the voltage drops across each of the capacitors once the capacitors have been reduced down to a simple series circuit here. So let's just double check. We know E is 30, V1 we found to be 1.15, and our V2 is 28.84. That is pretty close to 30. That is pretty close to 30. So that's a good check. We found the voltage drops across C1 and the equivalent capacitor of C2 and C3. We found this to be V1 is 1.15, and the voltage drop between these 2 points are going to be 28.84. The voltage drop across here is going to be the same. That is also going to be 28.84 between these 2 points because those two capacitors are in parallel. And at last we have our final answer, an equivalent capacitance of 0.769 nanofarads and voltage drops across C1, C2, and C3. That'll do it for this problem. Stay tuned for more in the future.